Hi everyone, welcome to the series of videos on applied statistics, and today we shall talk about how correlations can describe relationships in statistics. We shall build an intuition for the popular measures such as Pearson correlation and Spearman's correlation. So let's begin. To make sense of the world, we always connect different pieces of information. For example, we may want to see if it pays to study. Therefore, we want to see if the salary and the years of study in college have any connection. Likewise, do house prices change if the population of a city changes? Can body weight predict the age of death? Do different places have different infant mortality rates? Do air pollution levels increase the incidence of heart attack? Or does performance improve the salary, or are there other factors at play? Sometimes we also discover apparent connections that make no sense, like the number of films casting Nicolas Cage and the number of people drowning in the pools. Statistical tools and modern computing together can detect such strange connections, but such connections are called spurious correlations. Description of this video contains links to many such correlations. But to understand these connections, let us first revisit a more familiar type of relationship that we call the functional relationships. Functional relationships are well understood. For example, Fahrenheit temperature is Celsius temperature plus 32 times 9/5. Or an even simpler relationship could be simply y equals x. Or another example is y equals 2x. And this table shows many values of x and the corresponding values of y that are generated simply by multiplying x with 2. We can visualize this relationship, that is y equals 2x, by plotting all the xy pairs as points on this graph on your screen. Notice all these points fall on a straight line. Hence we call there is a linear association between x and y. Note, here x perfectly predicts y and vice versa. This is why it is called a functional or a deterministic relationship. By perfect prediction, we mean that if we choose any value of x, then we can exactly locate y. It's easy to see that if we select a value of y, then we can similarly locate x. There can be infinitely many linear relationships between x and y. 3 such linear relationships are shown on this slide. Here the numbers multiplying with x represents the slope of these lines. Clearly, the greater the number, the steeper the slope. In statistics, we often deal with less than perfect relationships though. To understand that, consider a situation where we do not know the relationship between two variables. Suppose we measure y after fixing a value of x. Then x is called the predictor, whereas y is the response. So for example, x could be global CO2 emissions and y can be global temperature. Then we want to see that when we know the value of x, how accurately can we predict y? Just to clarify, let's consider some sample data. This is the data that I've just generated using the R software. Here we have some values of x and some corresponding values of y. If we plot this data, we notice that it does not fall on a straight line. Or we say that a straight line does not fit the data. Therefore, if we try to use a straight line to describe this data, then the relationship is not exact. There is a hint of scatter. Overall, we see a trend that as x increases, y increases. If we try to find the best line to fit this data, it still only approximates the data. However, we may say that by and large, the data follows around this line, and so the data shows a linear trend. But you may say, which line should we use? After all, there may be many lines. Finding the best line is called linear regression, and that is the topic of our next video. But looking at these various lines, you can build an intuition that the line that is overall the closest to the data must be the best line. Unlike the functional relationships or the example you saw last time, in statistical relationships, sometimes there can be multiple values of a response variable for a given value of the predictor. For example, consider this map of the United States. Here the horizontal lines are called the latitude lines. The degree of latitude increases as we move away from the equator. Next, see this picture, which plots latitude along the x-axis and mortality rate with skin cancer on the y-axis. This picture shows that the mortality rate decreases as the latitude increases. This makes sense because the exposure to sun decreases when latitude increases. The credit for these pictures goes to Penn State University, and the link is also given in the description below. Note that the scatter here is even more than the scatter in the last slide. And the reason is that for each value of latitude, there are different values of the mortality rate. This is because these mortality rates are coming from different states that all fall on the same latitude line. Overall, despite the scatter, the top picture shows a decreasing trend. That is, as the latitude increases, the mortality rate decreases due to lower exposure to sun. However, sometimes the scatter is just too much, and we cannot spot any trend or a statistical relationship. Let's inspect that situation now. When the statistical variables are not related, they are called independent or dissociated variables. Independent variables cannot predict the values of each other because the scatter shows too much variation for each value of the predictor, and it's hard to see any trend. So to show that, suppose a variable b1 holds randomly generated numbers between 300 to 800, and b2 holds another set of randomly generated numbers between the same range. Do you think there will be a relationship? After all, they are coming from the same range, so you may be tempted to think that they grow together. Think about it. Now here's a sample that I drew. I used R to generate 100 numbers for each variable. A few numbers are on your screen. Now we can plot them to answer the question I asked. Do you think there is a relationship? As we plot the pairs of values from b1 and b2, we get almost a circular cloud. Note these numbers are generated randomly, so it is possible that your cloud looks slightly different from mine. But overall, you cannot say that there is a trend because for each value of a predictor b1, there are far too many values of b2. In this example, you can see that b2 takes almost the entire range of values, that is between 300 to 800, for a given value of b1. So how can you predict anything? To clarify even more, consider that if your friend asks you that for b1 equals 500, what value can you predict for b2? you will say B2 can be anything between 300 to 800, and therefore you cannot predict anything. The code to generate this plot is given in the description beneath this video. Now I invite you to experiment yourself. To do that, run this code in R. The code is also available in the description of this video. Note here your sample size equals 10. That is, you will generate 10 values for each variable. Note the ylim function in the last line finds the best line for the data, and abline function draws that line. Notice because the values of B1 and B2 are generated randomly, it will be useful to rerun the code a few times. You will notice that it will be more convenient for you to rerun the code if you encapsulate the code in a function. So that is a little exercise for you to improve your coding skills. Then finally, increase the value of x from 100 to 1000 to even much bigger values such as 100,000. Now your code will run slower for the large values of x because you are generating large sample sizes. So in that case, wait for the plots to appear. You need to discuss, when x is small, how the picture of the scatter changes. Can you see some trends sometimes? Do they stay after when you rerun? And what does that tell you about trusting a small dataset? Also, when x gets really big, your dataset gets really big as well. So do you see the scatter changing much at all during reruns with big datasets? You must think, what does that tell you about the reliability of a big dataset? So you can pause the video here if you haven't completed the exercise on the last slide, and move on to your R sessions, complete the exercise, draw the plots, and convince yourself what happens when the data is coming from independent variables and how the plots look like. This is really important for you to contrast a situation where there is a relationship versus where there isn't. Okay, so assuming that you have run your code, here are some sample results from me. For x equals 10, you can see that although the points are few, you cannot tell if the values on y-axis consistently increase or decrease as we go right on the x-axis. Instead, the values sort of oscillate or bounce up and down around the line, and therefore the line is flat. If we rerun this time around, there's a slight negative trend, but that is because of random effects of generating data. Overall, there is no clear trend. Occasionally, it may appear there is a strong positive trend, but again, this is the danger of using very small data sets. However, towards the right half of the graph, it is hard to see an overall trend. So that gives you an idea that there isn't really a trend. However, as we increase the data size to 100, a circular blob appears that rules out any trend. Increasing the data set size to 1000 or 100,000 makes it even clearer that there is no trend. In fact, a perfect square appears finally in the last plot that reinforces that for every value of x, every value of y is possible. Now, instead of a square, if instead a rectangle appears for you, that is because the size of x and y axes are not the same. So now that we have seen the statistical linear relationships, the question is, can we measure them? To do that, in statistics, we quantify how two variables vary together. Suppose x and y are continuous random variables. Then the covariance of x and y equals the expected value of the product of the deviations of x and y from their means. So x minus e of x shows how x varies from its mean value, that is e of x. And y minus ey shows how y varies from its mean value, that is e of y. Now if x and y deviate from their mean values at the same time, that is x and y values in an xy pair deviate from their respective mean values in a similar fashion, then this product will be big or high. However, if x deviates a lot from its mean, but y at that time deviates little, or vice versa, then the common sense tells us that the product will be small. And if this keeps happening most of the time, then the sum of these products will also be small, and therefore the covariance will be small. Now, if we have finite samples for x and y, and we pair different values of x and y, then we can compute the covariance in two ways. If we know the true population means, that is mu of x and mu of y, then we can compute the covariance of the observed samples as on your screens now. It is simply the average of products of deviations from their respective means. Here the average is taken by dividing by the sample size, that is n. If instead the true population means are not known, then we use sample means for x and y. Hence the formula is the same as above, except this time we divide by n minus 1 instead of n. Let us see an example. Suppose we have student scores for two modules, as on your screens, and we want to see if their performance across the two modules are related. So we want to compute their covariance. Here the class size is only 4 to fit the data on your screens, but normally you use much larger data sets to compute covariance reliably. Now, which of the two formulas on the last screen applies? Do we divide by n or n minus 1? To do that, you must ask yourself if the two populations are fully specified or not. Think about it. Well, the populations are indeed fully specified because we have the scores for the whole class. Therefore, we should use the first formula where we divide by n. If instead we had randomly sampled 4 scores out of, say, the scores for 25 students in the class, and nobody told us the true means of the class scores, then we should have used the second formula where we divided by n minus 1. So I'll leave it as an exercise for you to compute the covariances in each case. So pause the video here and compute the covariances. It's a good exercise to do it yourself and go through the motions of calculating. Okay, assume that you have done that. Now, in order to see if a linear trend exists, wherever possible, always try to plot the data, as we do here. Looks like there is a positive or increasing trend, as we can see the points going upwards as we move to the right side of the x-axis. Question is it linear? Well, looks like a line will be able to fit it with some approximation error. Now, compute the covariance as instructed on the last slide, if you haven't done it already. So, we get different results depending upon what formula we use. The sample covariance, though, is 216.667, whereas the population covariance is 162.5. The values are big, so perhaps they indicate a relationship. Now notice we said big values may indicate a strong relationship. But how far can it keep increasing? Notice covariance has this property that if the scale of even one variable increases, the overall covariance increases. This is represented on your screens where if I multiply x with a constant value a, that is if I increase all the scores for just, increase all the scores for just one of the variables by multiplying all of them with some constant value, then the overall covariance increases. This is rather strange, isn't it? Because we are looking for a relationship between two variables. And if we are multiplying only one of them with a constant value, ideologically, that doesn't say much about the relationship between the two of them. It's just, something that we uniformly apply to just one of the variables. But still, as we'll see, the covariance increases. So let me show. Suppose we double the marks obtained in the module B for everyone. This can happen if the grading scale is doubled. So for instance, instead of grading everyone out of 100, we grade everyone out of 200. Note, even so, the percentage of marks remain the same, but the raw scores have doubled. Now, according to the previous scale, the covariance was 162.5. But now on the new scale, the covariance between the two variables x and y suddenly jumps up to 324. So does that mean we now have a stronger relationship? This is absurd because nothing in the behavior of the data has changed. Therefore, to compare covariances across two data sets, we must ensure that their scales are the same. But there's a smarter way to deal with this. If we normalize or standardize the data, we bring all the data variables to the same scale. Hence, the data becomes what we call scale-invariant or unit-free. Remember, we can standardize a variable by using the formula that appears on your screens. Here, x is the variable in question, and mu of x is its mean value, whereas sigma of x is its standard deviation. Once we standardize the mean value of the variable, the mean value of the variable shifts down to 0. We can also show that even if we scale up the variable x by multiplying it with some constant a, its normalized score will still be the same as that of just the variable x. So let's see. For a times x, the z of ax equals ax minus a times the mean value of x. We also divide by the standard deviation, which is now a times the old standard deviation. Note here we are using properties of mean and standard deviation to compute these new values of mean and standard deviation for the new variable, which is a times x. So we can take the constant a out common in both the numerator and the denominator, and hence we get the same old z score. Pause the video if you want to just stare at these formulas or work through the algebraic manipulations yourself. Hence, z score is the same regardless of whether we have x or its scaled version, that is a times x. Hence, we have a unit-free or scale-invariant score now. Now, all we have to do is compute the covariance of the normalized variables. So, as before, the formula of covariance is on your screens. We then substitute the normalized versions of x and y, and we rearrange it a little bit. In case you're wondering why those zeros are appearing, that's because in the standardized versions, the mean values are always 0. So e of x and e of y are both 0 now. So, like I said, we rearrange it a little bit to finally get what is called covariance of x and y as before, divided by the product of standard deviations of x and y. This final form of covariance of the normalized variables has been extremely well known in statistics, and it is called Pearson's product moment coefficient. Now that was a mouthful to say, wasn't it? So we also call it just Pearson's correlation coefficient, or simply the correlation coefficient. It is represented by either the small r or the Greek letter rho that looks like a funny looking p. So while the derivation in the last page concerned expected values that take averages over the entire population, in practice we only deal with samples of data. And here's the formula for the samples, where x bar and y bar represent the sample means and Sx and Sy represent the sample standard deviations. Now R varies between -1 and 1, where -1 shows the maximum value of a decreasing linear relationship, that is, when x increases, y decreases and vice versa. Likewise, +1 shows the maximum value of an increasing linear relationship, whereas a value of 0 shows that there is no linear relationship at all and the variables are independent. Let us discuss the sign of the correlation coefficient with an example. Here we see how violent behavior in children increases as they see more and more violent scenes on TV or in videos. And as we can see in the figure, there is a positive relationship, and therefore the value of R equals plus 0.90. However, we can also compare the violent behavior with non-exposure to violent scenes, and then the relationship becomes decreasing and the sign of R value also turns negative. So the sign of R depends on how you frame the question. Therefore, it is common enough to square the value of R. This squared value has a special name, and it is the coefficient of determination. R squared simply tells the strength of the relationship but ignores the sign of a relationship. However, in your statistical analyses, it is important to describe whether the relationship is a positive or a negative one. Now, it is possible for a strong correlation to appear as a matter of chance. Therefore, we can conduct a hypothesis test on our computed values of R or R squared. If you want to refresh your understanding of what a hypothesis test is and how to conduct the hypothesis test in general, the link to those videos is in the description below. But we can use a t-test for this purpose with a degree of freedom set to n-2, where n equals number of data points. Here, the null hypothesis says that there is no correlation and R must be equal to 0. Whereas the t-test computes a p-value, and you can compare this p-value against your desired level of significance. And in R, you can use the function cor.test. It computes the correlation coefficient and its p-value. You can specify if you want to use a two-sided or one-sided test. The sample code is in the description below if you want to test the cor.test function. Now, a word of caution about the Pearson correlation. The Pearson correlation coefficient indicates the strength of a linear relationship between two variables, but its value generally does not completely characterize their relationship. For example, here we shall see 4 different plots that have an identical value of R and a pretty strong value actually of 0.816. Now, I borrow these plots from Wikipedia, so thank you, Wikipedia. They are famously known as the Anscombe's quartet, and the link is in the description of this video. The first plot shows a strong linear relationship. Although there is some oscillation around the line, generally y increases as x increases. But in the second plot, while y increases with x, and hence there is a relationship, this relationship does not look linear. Instead, it looks like a curve. Hence, the relationship is non-linear. Therefore, assuming a linear relationship will be error-prone. Instead, one should use non-linear regression, which is a topic beyond the present video, and compute R after that. In the third case, on the bottom left, the linear relationship is perfect except for one outlier which exerts enough influence to lower the correlation coefficient from 1 to 0.816. And in the fourth case, there is no relationship, but one outlier is enough to produce a high correlation. Here, if we had not seen the graph, we would have been fooled into believing that y varies with x linearly. These graphs were produced by a statistician, Francis Anscombe, in 1973 to highlight the importance of graphing and not relying simply on statistical numbers. That's the lesson for you. Wherever possible, accompany the graphs with your statistical computations. Note a famous quotation in statistics is that correlation is not causation. This means that just because we can see a high correlation, and even if the relationship visually looks linear, this does not mean one variable causes another. For example, this graph shows that as US spending on science and technology grew from 1999 to 2009, the number of suicides also raised. Notice the two curves grow very similarly, and therefore if you pair the data from these two curves and then plot, you will see a linear relationship. This is confirmed by a very high R value, which in this case is 0.997 or 99.7%. The credit for this graph goes to this website that is also linked in the description. Such correlations are called spurious correlations, and normally there is a third explanation behind such a strong correlation. This third explanation is called a confounder. For example, if ice creams are found on beaches, it does not imply that beaches produce the ice cream. Instead, it is probably the atmosphere that encourages the availability of ice creams. Hence, the atmosphere and proximity to the ice cream supply are the confounders. You can read up more about it by following the link from FutureLearn that also appears in the description. Finally, we discuss whether we can measure the strength of a nonlinear relationship. After all, we have been seeing nonlinear relationships in some of the plots that we've seen. That is, where the relationship is there but does not follow a straight line. One such measure is called the Spearman's rank correlation, and it is so called because it is often used with the ordinal or ranked variables. To remind you, the ordinal data comprises of rankings such as very poor, poor, okay, good, and very good. Sometimes ranks can be numerical as well, where, say, two different judges have ranked the performance of 10 participants as in the table below. Then the research question is, do these judges agree in their rankings consistently or not? We can compute the strength of that agreement with the Spearman's rank correlation. Also, as I said, Spearman's rank correlation detects nonlinear relationships. Basically, the Spearman's rank correlation checks if y grows as x grows. If this happens consistently, this is a monotonic relationship. To detect that, it converts the values x and y into ranks without ties. For example, in this plot from Wikipedia, although we have a nonlinear trend, it is a perfectly monotonic relationship. Therefore, Spearman's correlation is a perfect score of 1.0. Therefore, the Spearman's correlation is 1.0, whereas the Pearson's correlation is also high at 0.88, but is not perfect because the relationship is not linear. In the next plot, the presence of some outliers, I'm talking about the plot on the bottom left, the presence of some outliers on the right side lowers Pearson's correlation to 0.67, but the Spearman's correlation is still high at 0.84. Whereas in the last plot, on the bottom right, both the correlations are low because clearly there is no relation between the two variables, and this is why we are observing a blob, a circular blob almost. So remember, Spearman's correlation tests for a monotonic relationship only. Other than that, it tells you little about the nature of the relationship. In contrast, the Pearson's correlation does assume a linear relationship, and it always tells you the strength of a linear relationship. Finally, I'll quickly introduce Kendall's TOR. It is another ranked-based test. Like Spearman's correlation, it is a non-parametric test because it does not assume that the nature of the relationship is linear. It also checks if the two variables vary consistently together. Now, which one to use and which one is better in which circumstances, that is subject of research. But the important thing to remember is that while Pearson's correlation deals with continuous data, these two correlation measures deal with ordinal or ranked data. How to find associations between nominal data, the last kind of data, is left for your self-study. It may be covered in some future videos, but that's it for today. So thank you and see you in the next lecture. Bye.